Good morning, it's good to see you guys this morning again, and to this second class. Today's class in the solar course is going to be on design. In particular, the electrical system design more focused. Today, our guest lecturer is going to be Dr. David Martindale, and I'll let him introduce himself and his little background on that. But before we get started, let me open this with a word of prayer, if you would join me. Heavenly Father, thank you, Lord God, for bringing us here this morning. We thank you, God, for the sun that gives heat, light, and the things that make life possible on this planet. And we can tap into the energy of the sun and use it for electricity. And most importantly, we thank you for your Son, Jesus Christ, for the power that comes from Him alone. And it's not electric power, but it's a power that can live within us through His Holy Spirit. And I pray, God, you bless us this morning with your presence. Guide, direct us to bring you glory through this as we learn about this wonderful gift you've given us through the sun's energy. In Christ's name, amen. Last week we talked about what? What were some of the things you remember from last week when we got together? What were some of the things that we talked about last week?
The cost.
Talked about cost, yes, right. It's another thing. Goals.
Feedback.
Goals. Payback. What were you going to say about your Oh, I thought you were going to say. There were some other things we talked about last week. You were here last week.
Stewardship.
Stewardship, yes. That's right. Stewardship. What other things you remember? Other things stood out in your mind. Anything else? Yeah. David? Something started. Okay. Yeah. We were kind of looking at it from that initial standpoint of saying, hey, I hear about solar and I wonder if this thing would work for my family. And that was the kind of thing. And we looked at the return on investment and did it make sense and stewarding resources and trying to run through numbers. Mark, can you grab that? And yeah, we looked at that, and we were trying to get a gauge on, even if it's possible for it to make sense. Now we're at the point where we're saying, well, you know something, this thing looks like this is a possibility that this could make economic sense for our family. And so now we need to go a little bit further. We have some rough ideas of things. We were working with some numbers like, remember on the electrical side, we worked with wattages and how much electricity our family uses and how many watts we would produce in electric and solar and what that would mean cost-wise and return on investment. And now we need to go a little bit deeper and say, okay, well, how do you put this puzzle together if we're really going to do this? And so we need to look at the electrical side of things, the electrical engineering side of things, I would say. And so that's what we're going to look at today. And that's why Mr. Martindale is going to talk to you guys this morning and teach this class, because he's the expert in this and I'm not at all. I need to rely on his expertise for my help in doing this part of the design for our system. So I'm going to turn it over to him, and at the end I'll have a few other things to follow up on. But David, if you will, come in and class is yours.
Good morning. Good morning. I want each of you to ask questions anytime. Okay? First things first, do you know what electricity is? Does anybody have a definition of what it is? You know, we've been talking about electricity, but do we really know what it is? Yes?
A flow of electrons?
A flow of electrons, very good. And to make electrons flow, we have to get them excited, and we have to give them a path. A lot of times people relate electricity to water in a hose. It has to have pressure and volume and a place to go. It's quite a bit similar. The water in a hose has water pressure. Now that comes from a water tower being high in gravity, pushing the pressure. That's the voltage. The flow of the water comes out the end of the hose. That's the amperage. Volts, or voltage, times amperage is watts. And That's what we're talking about here is watts. So,
David?
Mhm.
So what did you relate, so you said pressure, volume, and flow is how we often talk about water,
yes,
and electricity similarly, and you were trying to relate the three,
yes.
and
Pressure is volts, flow is amps,
volume is wattage?
volume is wattage.
Got it.
Yeah. Okay. And what Eric touched on was last week we talked about the costs and the payback and that kind of stuff. And we talked about the energy. So we talked about producing 400 kilowatt hours per month. Well, to get to that, we need to produce about 3,100 watts for a little bit more than 4 hours a day. And you guys went through the math already of 4,000 times 4, 16 watt hours each day kind of thing. So what we need to do now is how do we build a system? And before we can build a system, we need to know what kinds there are and what types and what sizes there are. Because we have a rough target of 4,000 watts, okay? So we're going to break it down now and find out the different types. There's different types of solar panels. We brought the one that Eric's going to be using kind of thing. We brought that last week. In the papers that were passed out to you prior to the class, we presented there's thin film, poly, and mono silicates. They're different kinds of silicon. They've been impregnated with a circuit and different types of precious metals to create and stimulate the electrons when hit by sunlight. So sunlight hits these little panels and it makes the electrons excited. It makes them move out away from where their normal rotation or orbit is. When they get moved away, that's a potential. And when they fall back down, they let off energy. Another way of thinking about electricity is lightning. Benjamin Franklin saw the lightning and he tried to catch it. Well, what kind of energy was that? Well, that was DC, direct current. Electrons flowing from the ground up, but it looks like it comes down. And it's a lot of amperage and a lot of voltage. And if you walk across the carpet and you touch something, that's about 30,000 volts. That would kill a person. But it has no volume. It has high potential but no volume. When clouds are rubbing on the ionosphere and each other, they create a lot of surface tension and a lot of electricity, and then they create hundreds of thousands of volts. And they got a lot of surface area, so they got a lot of voltage, and they flow. But what we need to do here is we need to produce a steady voltage and current. And we're going to use I believe they're polysilicate.
Yes.
Poly type, multiple types of silicon on these panels. That's a type. Then we're going to cover size. The size of them, each of the little squares in series creates a voltage, about 2 volts. And you saw those little squares on the panel, and they're all wired in series, like a battery. But for today's experiment, or today's lesson, we're going to teach that each of these panels is a battery. And each of these little batteries, when put in the sun, and the sunlight hits it, it produces about 37 volts. And you were given here by Mark, I believe, the specifications page, the technical data page. And if you go to the far right, you'll see a D, on the top, you'll see a DLX 4.4 UL.
Hang on just a second, David. Has everybody got the right sheet?
Okay? And what we're going to look for here specifically is we're going to go down about a third of the page, and it's going to say VDC, normal operating range DC, direct current. Everybody find that? Okay, it's right there. What does DC mean? Mark?
Direct current.
Direct current. And the opposite of direct current would be alternating current. What does that look like in a wire? Direct current are the electrons moving from atom to atom to atom down the wire. And they keep moving that way until they get to their load, and then they come back and neutralize themselves on the negative terminal of the car battery or whatever's producing. So it's a direct path. Alternating current is what you get from your outlet. That's where the electrons go this way, then back, this way, and then back, 60 times a second in the United States. Europe's 50 in many places in Europe. The reason they created alternating current is because they're produced by a rotating magnet, and it passes the coil, then it goes, leaves the coil, passes the coil, leaves the coil. So the electrons want to go back and forth. That's alternating current. So, with DC, like a flashlight battery, I'm getting lots of different images for you so you can all get it. Flashlights have multiple batteries in them. Each of them is about 1 volt, 1.5 volts. You stack up your battery. Each time you add a battery, you're adding in series the voltage. So we got a 6 volt light bulb. We need to get to 6 volts, so we put like 5 or 4 batteries in there. So it'd be 1, 2, 3, 4 volts, half, 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 half. That gives you 6 volts. Now you have the right voltage to drive the flashlight. Similarly, when we go to the specifications on this data sheet, you'll see that normal operating range DC, 230 to 500 volts, okay? So we need to put our solar panels in series to get up to that voltage. So 37 volts, and I come off of the positive, go to the negative, come off the positive, go to the negative, come off the positive. We do that, 1, 2, 3, you should have 7 panels here in series. So 7 times 37 is what? Who can do that real quick? 259, okay. And 259 is in the range of the operating range. So when the sun comes up and hits these panels, they're going to pop up to 37 volts, and it'll be in the operating range of the inverter. That satisfies voltage. Now we're going to ask the question, what's the current? The current of a solar panel is very interesting. The current of a solar panel depends on the incident angle of the sun. So if this is my solar panel, and the sun's over here, and the sun's hit, am I going to produce very much? No. So in the morning, the power coming out of the panel will start really low. And as the sun gets up perpendicular, it'll be at its maximum. Maximum is 90-degree angle to the panel. Okay?
What is current?
Current is the amount of electrons flowing.
So that's wattage then?
No.
No?
The amount of electrons flowing is current, amps. Volume.
Oh, okay, okay.
Okay? We have to have the sun first to get potential voltage, and then the amount of current depends on the angle of the sun on the panel. The more closely perpendicular, the more those photons and electrons that are hitting the panel from the sun, they're getting there and it's producing the current. Okay? So you already have the voltage, now you need the current. So you've got volts times amps equals watts. If you get anything out of this lesson, get that. Volts times amps equals watts. And we're dealing with single phase power here, so there's no square root of 3 or power factor involved. So we're going to keep it simple. So as the sun becomes more perpendicular to the panel, the amperage goes up. Voltage is already there. Yes? Looks like you have a question or a comment. No? Okay. Now here's another big concept. I know I'm going out of order on the outline. Here's another big concept. When you're designing a system or even building a system, you have to make sure each piece is happy. Okay? We can't apply voltage to this because this is a voltage source. We can't put a skinny wire here that won't handle 8 amps because the wire will eat up and melt away like a welder stick. We don't want to use too heavy of a wire because it's too expensive. So we need, let's say, a number 14 wire or number 12 wire, which is standard household wire. Because a household wire, number 14, will handle 15 amps. That gives us a big safety factor. So the wire's gotta be happy, the solar panel's gotta be happy, and then we really gotta make sure that the inverter's happy. And the way we make the inverter happy is we have to stay within the specifications of the piece of equipment. And the piece of equipment says we can give it 230 to 500 volts, but then it also says, we go a little further down, I'm looking for DC amps. And I didn't look this up ahead of time, but it should be in here. Current DC. There you go, maximum operating input current, 21 amps. About halfway down the page, maximum operating current on this model, 4.4, is 21 amps. And we're gonna give it 2 strings of 7 amps. So we'll be at 14, 15 amps, so we're below 21, so the inverter should be generally functional. We have to design the system for worst case scenario or best case scenario. Worst case scenario is it's dark out. Best case scenario is the sun is shining on it, perfectly perpendicular, and it's cold out. This is a transistor. The solar panels are a computer chip, basically. And computer chips like to be cold. They don't like to be hot. They produce more. They actually produce up to 20% more power than nameplate when they're cold. So, best case scenario, sun's shining directly at them, and it's minus 20 degrees outside. So now, my amperage is no longer 17 amps. It's 17 plus 20%. Does that fit with our inverter? Let's see here.
Actually, 14 plus.
Sorry.
Yeah.
14, yeah, 7. Maximum operating current, 21 amps. So what's 1.2 times 14?
Oh,
2% more than 14 is another 2 or 3 amps. So we're
Yeah.
still below the 20, 21. There you go. A lot of engineers make that mistake, and you just size it for what the nameplate is. Well, the nameplate on solar panels is sized at full sun, 70 degrees. So when you buy something electrical, what is the parameters its intention is for? We have to stay within those boundaries. If we go outside of those boundaries, then we're setting up a dangerous situation that can cause a fire and burn your house down. That would not be being a good steward. So being a good steward involves money many times, but it also involves caution and wisdom and knowledge about what you're working on. So when Eric says he doesn't know about how to do this a little bit in parts and pieces, he reaches out and finds somebody that does. And that is another huge lesson for anybody that's doing things. If I'm gonna go and try and sew a suit on a sewing machine, I know how to plug the sewing machine in, but I don't know how to operate it. So it would be really a bad stewardship if I'm gonna start cutting fabric and sewing it, because I'm gonna do a terrible job. And I would be wasting material. If Eric didn't reach out to somebody that he knew how to do this, he'd be wasting his time and money, and that's not good stewardship, right? So you can look at it at the positive side and the negative side. The point I'm trying to make is reach out to somebody that does know, learn from others that have experienced it and done it. That's my point. Okay.
This might be a rabbit trail, but it sounds like you had a whole system of these in the Arctic, like someplace quite cold where you have like a desert climate, if you will, not much snowfall. It's like you'd be better off, because you said they work better in colder climates, lower temperatures.
Yeah.
You could have something where you capture energy in a place that like nobody can inhabit, and yet it seems like it'd be a little more efficient.
It would be. There's a lot of snowfall in the Arctic.
Well, you get a desert, like in some places it's desert conditions in cold places.
That's true.
So you can find a spot that would have more of the desert type climate to it.
Okay. And how many people are there to use that electricity?
No, it's some way to harness it out. You could put it in a battery or something that you could transfer in and out, you know what I mean? But it's like something like that. It's
yeah, because that'd be the best place to produce it is where it's.
That's what I'm
cold.
saying, yeah, it sounds like that's, but, yeah, capturing energy and having it transferred is your issue.
Two different issues. Yeah.
Right, yeah.
Transportation Transportation is a big deal,
Yeah, oh, I'm sure, yes.
especially with electricity. Okay, so I'm gonna transition into what this system is. This is what's called an on-grid system.
What are we looking at there, Dave, by the
Right.
way?
Yeah,
I'm
thank you.
sorry.
We're gonna walk through this. We've talked about the panels and how to build up the voltage. We've talked about having the wire the right size and the current, making sure that the inverter is happy on the DC side. So what we're doing here is we're connecting each of the solar panels together. You've got this in front of you to get the voltage up. Now we've got 270 volts or so, and we're at around 15 amps as a total coming in. So we got the DC, the direct current side, sort of completed. Now, there's fuses here, and that's in case something shorts out somewhere or lightning strikes. We want these fuses to blow and protect the inverter, because this costs a couple $1,000. We don't want to wreck it. And this is outdoors, can be outdoors or indoors. So if lightning strikes here, you're going to see there's a ground wire, the green wire connects to a ground rod line. So the aluminum frame of these inverters, we want that to be the potential earth, because that's where lightning wants to go, is get neutralized. So now we've got the DC side done. Let's look at the AC side. The utility company, they've spent a lot of money and time bringing wire to your house, to the factories, to the hospital. They own those wires. They own those transformers, the poles. They have easements on property, legal rights to everything. So we really can't connect another source of power to anything that's connected to the utility. Here's the utility up here, this is your utility meter. The wire's coming into the meter on your house, you're all familiar with the meter on your house. They own the meter, you own the socket, and that's the line of demarcation right there. Okay? They own this, you own that. You're not going to connect anything that produces power to their wires without their permission. And this is a big deal. A big deal for me in my career, because I was building big power plants for hospitals and factories, and they didn't like it because, see, they make their money selling you power. If you make your own power, you're not buying theirs. And they don't like that because they want you to buy their power, supply and demand. So you've got to get permission from them to hook up this. Well, these inverters are sort of new. They've been around a few years. There's different kinds. I'm going to get to that other kind shortly. But this is an on-grid system. An on-grid system means you're producing the power here in DC. The inverter takes it from direct current and makes it into alternating current. And that hasn't been able to be done until just the last 20, 30 years. And now they've really, the worldwide market for solar panels has forced the utilities to accept this interconnection, is what it's called, by virtue of making a standard. And I'll describe the standard here in a minute. But you need to understand what we're doing. We're going from DC to AC, and we're going to make 120 volts from here to ground and 120 volts from there to ground. So there's an L1 and an L2 on your drawing. One of these outlets in the room is connected to one of these wires off of a breaker in your house, and then maybe a different outlet somewhere is connected to the other leg. So you got 120 to ground on this leg and 120 to ground on that leg. Between the two, you got 240 volts. Okay, now I'm going to skip all the technicalities of that, but that's the voltage. You don't want to put your tongue on it. If you put your finger on it, you're going to feel it. It won't kill you usually. Let's put it that way. So now that you got power coming here, you've taken it from DC to AC, you got power coming here. This is your main power panel in your basement. And you're going to wire it to a 30 amp breaker, plus or minus. Could go 20 amps, whatever. Why don't we do that example real quick? What's 4,400 divided by 240? Okay, less than 20? Yeah, we can do a 20 amp breaker there or a 30 amp breaker. The purpose of the breaker is if Eric sticks his screwdriver in here when it's hot and shorts it out, we don't want that power to keep flowing through Eric's screwdriver. we want this breaker to open up and shut the power off so Eric doesn't get more electrocuted. We don't mind electrocuting Eric for a moment, but we don't want to kill him. Yes,
And the breaker really protects either way too. If we were taking, if we had a short
good
taking,
question.
and if we were producing too much, we would trip the breaker?
Good question. It depends on where the fault is. Did the person stick the screwdriver here and this power is going to flow that way? But this power is also going to flow that way. Those fuses might pop, this is going to pop. So if the fault's over here, that breaker is going to have to protect the person. Not, and this one may or may not. It depends.
Okay.
It depends on where the fault is. That's a tricky question. That's a very tricky question. It's called an arc flash study.
Can I also ask another question?
Okay. So now let's pretend that the house has no loads. Everything's turned off in the house. But it's noontime and this thing's cranking out power. Where's the power going to go? Is it going to go down here to all the loads in the house? There's no loads in the house. Where's it going to go? It's going to go out to the utility. It's going to spin that meter backwards. It really will. Unless you have a digital meter, then it records it on a different channel. And that's a good thing, because now, when your meter spins backwards, you go throughout the day, the sun goes down, the loads in your house now are going to start spinning that meter forward. Oh, wait a minute. I'm not. Am I paying for that power? I spun it backwards. I already got charged for it once. So now I'm just sort of catching up. It's like trying to run your odometer in your car backwards. You already paid for that power the first time. You don't have to pay for it the second time if it came in there. So that's a good thing.
It runs 2.5 times faster the other way.
Economically, it does, but in the physicals, it doesn't. So my point is we have to make sure that each piece is happy. The utility, the breaker sizes, the wire sizes, the inverter size, the amperage and voltage, the wire size, and the panel size.
What is that drawing called, David?
This is called a one-line diagram. In actuality, it's a little bit more than a one-line because we're showing both sides. But we're just showing the power path of where the basic components are, and we're putting down the parameters of each component in its basic form. The details are in the cut sheets, the data sheets of each piece of equipment. Some of this stuff is existing, some of it's new, and that's why it's tagged as existing, new. This is a simple diagram that gives you a plan. Where you physically put this doesn't matter electrically, unless you're really a long distance away from, like hundreds of feet. Where you put this doesn't matter to this diagram. It can be 50, 60 feet from wherever. As long as you're not creating super long electric runs where you're lowering your voltage, because copper does have resistance. Wires are copper, so you do need to overcome that. If you go out, you put this, let's say 3,000 feet from this, which wouldn't make any sense, well, then you're going to have a voltage drop to overcome on that wire. So this is called a one line. And this would be what gets presented along with the specifications to both the utility, to local jurisdictional authority. Local authority having jurisdiction, that's the technical term for it, would be your local electrical inspector of your township or your city or whatever. Any questions so far? Okay, we're going to flip now to, oh, one question, yes, Mark?
So if you did have the panels a long ways away, what would be some ways that you could overcome the voltage drop?
A larger wire size. The cross section of a piece of wire is, let's say it's that big around, okay, in a microscope. I can only push so much water through the garden hose, okay? If that was water, we're pushing electricity, it's water, I got a hose that big. And I only have so much voltage, because this is only going to produce the 270 volts. That's only so much water pressure in the water analogy. And if that hose is really, really long, I'm not going to be able to push as much water through it. If it's short, I can push more water through it. Or electricity, whichever analogy you want to use. So the way to get around that is to go to a bigger wire size. It gives you less resistance, and you can push more power through it, or cover more distance. Okay? So, early solar panels were designed for satellites and such, and then transitioned down to terrestrial or Earth, and people out in the mountains, or where there was no electrical company, wanted to have electricity. So they would build what's called an off-grid system. The off-grid system didn't have the utility at all, okay? They had solar panels, an inverter, and they had another piece that was called the charge controller, and it would charge batteries. So they charge their batteries in the day, and then use a little bit of the battery power at night, and put it over to a load. But you didn't have this interface. So you didn't have to deal with the utility, you didn't have to deal with synchronization between this device and this device. But you had the batteries. Those are called an off-grid system. Nowadays, they have hybrid systems, which are off-grid, on-grid. They have the batteries also, and they will disconnect the utility when the utility's gone, and you can charge the batteries from the utility, you can charge the batteries from the solar panels, you can do lots of different things with hybrid systems. But this system is a straightforward on-grid system. Okay. The next topic is, what does an inverter do? Now, this is where I need my new piece of paper. Some people say the devil's in the details, and I like to say sometimes the blessing's in the details. We're going to go from DC power to AC power. That's the symbol, okay, of the inverter. Now, this is the hardest part to try and teach. It's the hardest concept. These inverters I'm trying to create that waveform. This is Eric Skelton's system over here. And over on this side is the utility. It's producing power. It goes up to over 120 volts and then down to a negative 120 volts. And it's going to do that 60 times a second at 60 hertz. It's frequency. Okay? I got to get from this to this, and I need this to match up in time exactly the same as that. So if I'm at this moment in time, I need that to be that moment in time. If I connect them out of phase, it's going to go kaboom. It's going to spark. It's going to blow up. So what the inverter does, and I'll make a big view of it here, what the inverter does is it tries to make that shape by creating little pulses. You see the sine wave showing up? This is a simplification of what's going on. But that inverter is turning on and off thousands of times a second and producing different little chunks of DC power. Very, very fast. And it looks like a sine wave. And because it's producing these little pulses when it wants to, it looks at the utility and says, I need to produce this moment of power right there. And that's what it cranks up, is it cranks up that little piece. And when that pattern produced by the inverter matches the utility's pattern, and they're in time, the transistors close and they connect. See where I can do that. Internal to here, it has the utility side, and then over here is the inverter. It connects them with the transistors and says, okay, I'm happy. I can see the utility, I can see the DC, they're in phase, I can produce the same waveform. Okay. Now here comes the magic. I need to take my power from the solar panels and I need to push against the utility so that the utility power incoming is reduced. Let me jump over to the water hose example. How am I going to take that water hose, which has a pressure, this water hose that has a pressure, and make the load of the house use this power, all of it, and not use that one? It's sort of an easy question if you think about water hoses. Any answers?
Squeeze it off.
Okay, let's think about the opposite. Not squeeze it off, because I can't squeeze the wire. Okay? If I made this water pressure higher than that water pressure, what would happen?
Push it the other way. You push it.
This water will flow more, this water will flow less. And what's the equivalent to water pressure and electricity?
Voltage.
Voltage. You got it. So, coming back to here now, I need my inverter to go a little bit higher on every pulse than what the utilities is. And when it does that, all that energy that's sitting right here continuously from the sun flows into this panel, and this reduces it because its water pressure is there. This pressure is higher, voltage is higher. This power now the amperage starts flowing here. This amperage gets reduced. Think about having two garden hoses hooked to the same sprinkler. The one with the highest water pressure is going to have the most water flowing through it. Okay? That's the magic of it and the trick of it. The other piece of the puzzle is this. These inverters, I think you guys saw it last year when we had it in here, last week when we were in here. These inverters are very heavy. They have a lot of capacitors in them because they have to take this energy, all that solar panel energy, they have to take it here. If they don't take it, where does it go? Okay, they have to turn off those solar panels. And so they have a lot of capacitors in them that absorb those inrushes and outrushes and sort of dampen the system. It's like having a big, big bucket of water. And the solar panels are throwing water in, and somebody comes along and disconnects this breaker or that breaker. Well, what do? I'm still taking that water in. It's flowing in. Wait a minute, I gotta stop. And it shuts it off. It gives it a few milliseconds to respond. That's why there's a lot of capacitors in there, a lot of energy. It's like a little battery. Capacitors are like batteries. So the capacitors give it a chance to respond a few seconds. If you didn't have the capacitance, it would just blow up. You can't respond that fast. So it acts like a giant barrel of water. You can take it in, hold it for a little bit, and then shut the valve off. I can push it out, make sure it's working, and then start refilling it. So it gives it a reservoir of energy to work with to maneuver this pulses up and down so that it's taking the power from the solar panels or not taking the power from the solar panels.
So Dave?
Yeah.
So when the solar panels are really cranking out high noon, those pulses get even higher then?
No,
It's just stronger than the,
it has, they will be big enough or just above enough of the utility, bigger than the utility, so that all of the amperage, the 15 amps coming in here, is used. Another way of looking at it is, you got that big bathtub of water, which is their capacitors. They don't want those to overflow. If they get too high, it'll shut down. So it's gonna drain those capacitors in that split second. It'll push this high enough so that it gets used up. And if it needs to, because it doesn't know what the load is. This device does not know what's going on over here. All it can see is the voltage of the wires. So if that voltage of the wires goes higher, this is gonna go higher. If this goes lower, let's say your neighbor down the street turns on a big motor or something, this goes, he's running a big welder or something, 3 houses down, this voltage is gonna go down. This will go down until this is used, just balanced, so they respond happily. Now, let's say somebody's car hits the intersection, knocks the pole down, and this gets knocked out. Does Eric have power?
Is it sunny out?
Yes. Good question. It is sunny out. Yes, Mark?
No,
Why?
because there's no power coming in. And so it doesn't have somewhere for the power to go.
Sort of. We locked out the utility, that power could go to the loads, right? But here's where we hit a safety issue. This is an on-grid system. This inverter needs a reference point. Its reference point is the utility. If the utility disappears, that means that voltage is dropping. It goes below the threshold of safety on this inverter, which I think is 208, 208. VAC under voltage, low level, trip level, 208, yep. If that 220 volts drops to 208, the inverter shuts off. When it shuts off, then it shunts the solar panels so that that current is doing this, and its little water tank is full and it can't do anything, it's disappeared. That's an on-grid system. If you had an off-grid system, that energy then would go to the batteries, and the charge controllers would take the AC, convert it back to DC, and charge whatever battery system you had. We don't have that. So being an on-grid system, it needs a reference point. That's the key to that answer. And it's lost its reference point, so it shuts off. So when does it come back on? Well, here's where we come to that interconnection standard, where we've been able to force the utilities to accept this power by creating a worldwide international standard that says, hey, this device, the inverter, is going to wait for 5 minutes after it sees new power. So the inverter is going to stay off as long as the utility is knocked out. Okay, so the guys come out, they fix the pole, they turn the power back on, boom, start the timer. Power's back onto the house, this is off, power's coming from the utility like every normal house, count down to 5 minutes. When 5 minutes gets here, the inverter goes, yep, timer's over, do I have power? Yep, I've got power. Oh, well then I should do something with my solar power. I got 4,000 watts of power sitting here. I gotta do something with it. So it goes, synchronizes, connects and says, oh, I'm okay. It's within voltage parameters. It's not low, it's not high. I'll push a little bit of power. And it raises it just a teeny bit. Throws out a couple hundred watts. Everything's still good. Oof. It starts opening that water valve on that big bathtub and it starts throwing that amperage out there and letting that water flow out. And it says, okay, go. And it starts taking it from the solar panels. That all happens in about 7 seconds. After the 5-minute timer is over. That's the safety standard. The reason the safety standard is there is because if I got a line coming down the road here, and every little house has a transformer, and it converts it from 5,000 volts down to 220, and I got every little house down the road here, and let's say the semi takes out that pole. Oh, wait a minute, this guy over here, he's got solar panels. So the wireman comes out here, he puts up his ladder, and he's going to grab this wire and grab that wire, put them together, and tighten his hex bolts or his unions or whatever he's doing. As soon as he grabs that wire, if this wasn't off the grid, he's going to get hit with 5,000 volts. Now you have a dead electrician. Literally. That's why these things are expensive, and then why they developed a standard, because if that's an on-grid inverter, this thing doesn't have any voltage, this has got to be offline, and it's offline by the inverter. There's your inverter. That's why it took 15 years to develop a standard to make all the utilities in the entire world happy. It was a tough task. It's taken 15 plus years to get there. Okay. The next topic is to match the inverter to the panels. We've already talked about that a little bit, so let's do a little review. In our system, we wanted 4,000 watts. Why would we get an inverter that's bigger than 4,000 watts? We've got a 4,400 watt inverter. I have given you the answer about 20 minutes ago. Mark?
Because if it gets colder, then the solar panels produce more power.
Correct. There's different kinds of inverters. Some inverters will actually go more than their nameplate. And they'll go more than their nameplate until they burn up or those fuses blow. Right here. This Danfoss inverter has the ability to take more panels. And I could put on, let's say I could put on 5,000 watts here. I could put another 2 or 3 panels on this circuit and 2 or 3 panels on this circuit. I'd still be within my voltage parameters because I can go to 500 volts DC. And now I'd say I have a 5,000 watt system hooked to a 4,400 watt inverter. What's going to happen with that other 600 watts? In this particular inverter, it's going to heat sink it. It's going to dissipate it in the metal fins that the chassis is built on. It'll take that excess energy and dump it to heat and get rid of it. It's not a good design. It's not the right way to do it. It's not efficient because you spent money on panels that you didn't need. Okay? And then the heat's getting dissipated. It does have the advantage though, because in low angle sun, where you're not, right at it, you'll be producing more power during those shoulder hours of the sun, morning till evening of the sun. You'd be producing more power over here and here, but when you get to the peak of the day, you're really pushing your inverter to dissipate that heat. And you could overdrive it. So you want to be, like I said, 20% less than your nominal inverter size, because on those cold, sunny days, you'll be right up to the peak. Are there any questions? Okay. 11 o'clock. We're halfway through and I'm already almost done. So, this is a meter we'll be using. Has anybody ever used a voltmeter before or amp meter? Monster, you have? Pass this around. You measure voltage by touching the ground and the hot terminal. Okay, the metal conducts electricity, plastic doesn't. You didn't know that? You can set it to amperage, and then you can clamp this on your wire, and it'll measure the amperage going through the wire. Okay? You can pass it around. That is a way of safely figuring out if each piece is working. Once you guys start building this rack out in the backyard, you have to think, oh, okay, the rack's up, we're going to mount the panel. Mount the panel. There's 2 wires coming off the panel. Is there voltage on those wires? Yeah. It's in the sun, there's voltage on those wires. And you can check it. Now I start hooking them together. oh, what's the voltage between here and here? 270 volts. If you touch those wires, you're gonna really feel it. They're insulated, they're made so you can handle them, and the wire isn't exposed. They're sort of hidden shell pin kind of thing. So it's safe, but you gotta be careful too. Once you hook them to the inverter, is that current gonna flow? Probably not until you hook this up. And it's been there for 5 minutes. This particular inverter is meant for multiple types of systems. It can do 208 3-phase on 2 legs, or it can do 220 and do a grounded neutral or a single phase. So we have to program this inverter. When we get to that in probably about a month, less than a month maybe, it depends on Eric, you guys, when you get your system built. So we have to program this for the right voltage and stuff. And then we've got a wire from the inverter. This is the next topic on your list here, connection to the house. You're gonna probably bury a wire mark, right? Is that what I've heard you guys say? You're gonna bury a wire from the inverter into the house and connect it to a new breaker in the house. So that's why we said direct burial Romex here for the electrical inspector to explain to them what we plan on doing. I didn't draw a floor plan for Eric, a site plan for Eric. That's your guys' thing and where you're gonna position it. He knew how to do that, he knew where he wanted it. You guys know what trees to take down if they're in the way. And next week you're gonna be covering this device. Gonna take it outside and you're gonna pass this around. You're gonna get it level. You're gonna aim it south. And you're gonna put the dome on. And you're gonna look at the dome. And you're gonna see where the shadows are on the plastic. And you're gonna reflect that onto this piece of paper. And Eric's gonna show you outside that each of these lines is a particular month. I'm gonna show you conceptually what I'm talking about. You hold it this way. And in December, the sun is way down there. Well, we say the sun's way down there, but in actuality, we're tilted and we're over here. Okay. And in June, the sun is way high. So each month, the angle that it comes up and sweeps over this latitude, about 42 and a half degrees latitude, is different. And then these vertical lines mark the hour of the day. And when you look into the plastic, you'll see a tree or a roof of a house. It'll throw a shadow on the plastic, and you can mark the piece of paper down here. And oh, okay, I've got a tree blocking at 7 a.m. in June through March or whatever, and you can mark. So that means that if I put my solar panel here, that particular time period, I'm going to shadow my inverter's power. And I'll pass that around. You get a feel for that. And then next week you'll go outside and work with that. Unless Mark wants to, or else Eric wants to do that today. So, is there anything? I mean, I ran through it pretty fast. What do you want to cover over again or expand upon?
Could you expand upon off-grid battery type?
Okay. Sure. In an off-grid system, you have panels, you have an inverter, you have a charge controller, and you have batteries. Batteries are the most expensive thing. Okay? Typically, they're lead-acid batteries, which are like large car batteries. In the daytime, the DC gets converted to AC just like before, and there may or may not be load in the daytime. Most off-grid people are using the sunlight, so they don't turn their lights on during the day. So they know that they need to charge their batteries during the day. So the power goes in, goes from DC to AC, and this inverter can take the DC. If it's not going over to a load, the DC, or whatever portion, it's a blend, the portion of DC can come down here to the charge controller and charge the batteries. The charge controller is the same as a battery charger, except instead of taking AC in, it'll take DC in. You can get them either way. You can put the charge controller over here or here, depends on the charge controller you buy. Typically, it's more efficient just to take it to the DC side. So it'll take, let's say it'll take 48 volts DC, and it'll convert it to 12 volts DC, and charge a standard 12 volt battery. You can put a whole bunch of 12 volt batteries in parallel, because parallel means all the positives are connected together, so you're just creating bigger volume. Or if you were going to take the batteries and put them in series, 12 volt battery in series with a 12 volt battery is 24 volts, and series with another 12 volt battery is 36 volts, and so on and so forth. So when the sun goes down, solar panels aren't producing anything, but the batteries are available, and then it comes back up through the inverter to produce AC. The batteries becomes a critical component then. You can only discharge a deep cell battery about 50%. Batteries are sized in what's called amp hours. So if you had a 1,000 amp hour battery, you could really only use 500 amp hours out of it. Before the voltage goes from 12 volts down to like 9. You can take it down to 12 down and still function. The inverters will still function, but you have to keep the inverter happy. It needs a voltage threshold. Is this the kind of information you were looking for? Okay.
Also, does the battery, after, or if you're taking from the battery, does it have to go back through the charge controller? The opposite way? Or-
No. There's actually another connection from the battery. It actually comes up and goes to the inverter. There's another wire I didn't draw. It depends on your charge controller, but usually there's another heavy wire. And because you're dealing with a lower voltage here in your battery, you're dealing with 24 or 12 volt batteries typically, maybe sometimes 48. The wire size goes from a little skinny number 12 up to a 300 MCM. I mean, literally the cable can be that big. Because you reduce the voltage, to get the same power, you've got to increase the amperage. And since batteries are generally lower voltage, you have to, that's a real heavy wire. I mean, it's the size of my thumb, at least, to go from the battery up to this off-grid inverter. But then out of the inverter, then you're back down to your standard number 10 or 12 wire over to your load bank. Mark had asked about off-grid inverters, on what the concepts are there. The biggest deal there is battery volume and type. We covered site selection a little bit. I passed the thing around, explained that a little bit, so that when you do it, you can actually go outside and do it wherever you want. And next time you'll also be counting the mounting system. Last week we covered costs, and if you were to take your dollars of your investment, you're going to spend a third of it in panels, a third of it in the mounting, and a third of it in the labor. typically is how it goes. And by building the system yourself, you just save 33%. Okay? We talked about wiring to the inside of the house over to the panel. There's different kinds of wire. Your outdoor wire is UV protected, meaning the plastic that it's in is, the sunlight doesn't break down the plastic. Where regular interior wiring, be it straight wire or Romex, you put that out in the sunlight, you give it about 2 years and the thing will just fall apart. I mean, voltage will come right through that plastic and start shorting out. I live on a farm and we actually had that happen where I didn't put my Romex in a conduit, and 4 years later it's like making static. I'm standing next to it, I'm hearing it, going, what is going on? Found it, I'm like, oh boy, I didn't do that right. So, you gotta use the right material for the right application. And that's where Eric's got experience in building things, and you don't wanna take shortcuts where nature and the environment are gonna degrade your equipment so it's not safe. You wanna make it safe because, see, the system is not gonna be on the roof, it's gonna be at grade level. And you guys are gonna be on vacation or traveling somewhere, and it doesn't prevent somebody with a little 4-year-old from walking across the church, across the road, coming over here and touching things. And if they touch something and it wasn't built to reasonable efforts, proper equipment, then you're gonna be held liable for injury. So there are standards you need to follow. And that's why they make National Electrical Code standards, to try to build things so they don't hurt people. When we drive down the road, we trust that that bridge is gonna hold us up, right? If engineers don't know the stresses and the weight loads and the live loads and the dead loads of what travels across that bridge, people are gonna get hurt. And so that's why there's engineers, so that the primary, you know how doctors have, you know, the do no harm kind of mantra. Engineers have a similar one, is to keep the public safety at the foremost of their mind, is to build things that are safe and functional and usable. And if we build things that are unsafe, we lose our job, we lose our career. So you have to build things that are safe. So when you do it yourself, you also want to keep that in mind, because you don't want to get hurt building it. And building a solar system is safe, but also inherently dangerous. Because our bodies run at about between 0.5 volt and 1.5 volts. Our muscles are triggered by electricity created in our bodies through energy. And our brain fires off our muscles. So when I accidentally touch 120 volts, the muscles in my arm will tighten up and thrust in one direction, depending on where you get touched with electricity. That's 100 times the energy that your body is normally operating at. Now, if I touch a 12-volt car battery, I'm not going to feel anything. Your hands are dry, there's dirt on the terminals, you don't have really good contact. If you had an open wound here and an open wound here and you touched a car battery, it would cause your heart muscle to go and you would die on a 12-volt car battery. That's a fact.
Really?
Yep.
Wow.
If you take a 9-volt battery that runs your smoke detector, you touch it with your tongue, it goes, I mean, you can feel it. Okay, that's DC. Your tongue is a muscle. You're causing your tongue to go. So electricity, my point is electricity is real, not seeable. You can't see it like a water hose. I use the water and the hose as an example, but because you can see that, you know, yeah, I can watch out for it. But you can walk up to a wire on a telephone pole, if you didn't realize, if you hadn't been trained, and you'd see those wires laying on the ground, and you're just walking across the park, oh, wires. I don't know that that's electricity, no one's taught me anything about electricity, and you're gonna play with it or whatever, you can get killed. That's 5,000 volts or maybe 12,000 volts. So electricity is inherently safe, but it's inherently dangerous too. And there's nothing to be afraid of as long as you know what you're doing. It's like bowling. You got a bowling ball. It's inherently safe and it's inherently dangerous. I put it on the floor, it's not going to do anything. I hold it in the air, oh wait a minute, it has energy now. If I let go of it, it has energy. Am I putting away? Oh, now it's dangerous. It's the same as electricity. So you just have to be aware of what's going on. Another safety rule is don't turn anything on unless you check with other people. We call it a lockout tagout procedure. I don't know if the older gentlemen have experienced that. You can, a lot of people just put tape over switches and okay, fine. You're trusting that the next silly person that comes up doesn't ignore the piece of tape and turns it on while you're in a cabinet working on something. So Eric's probably going to use tape and he's going to tape the breaker shut and tell you don't turn this on because we're out in the yard working on it, and if you turn that on we're going to have 220 volts in our hands. So don't turn things on unless you've checked with what's going on with other people. Okay? So basic things. I don't have anything else there.
Okay, I had a few questions too, if you want to stick.
Yeah, please.
For you, and maybe that'll help, too.
There are no moving parts in a PV system, except for one thing. What's the moving thing? Hmm?
The sun is moving.
That's moving, yeah. The electrons, very good. That's paying attention.
Yeah, that's right. Yeah, thanks, Dave. So, so a couple of questions for you, and I don't know if you covered this, but just kind of review. One of the things when I was working on this element of the design and talking with you, so I selected the solar panels I want to use. And again, I think I mentioned before that for me, I was looking for the highest wattage panel that I could get. That was really kind of the thing because then I was maximizing my square footage. So that's all right. So here I got, I want 4,000 watts of power basically, and so I'm going to get enough panels to make 4,000 watts. All right, I got that. That's simple. But now I got to hook it into my inverter, and so there are two things that Dave had to help me understand in terms of design to figure out how to make this work. And so he was pointing out, I put in your things there, the solar panel specs, and I don't know that you.
I didn't have it. No, good.
Okay. Yeah. So, you're going to have to help me here because what we looked at on this solar panel spec sheet is we looked at there's going to be two things that go into the inverter that matter that you got to kind of balance out. And Mr. Martindale did cover it already, but it's going to deal with volts and amps, I believe, is what we got to do. And so we got to figure out a way to get these. I want all these panels. I want 4,000 watts. How am I going to make the inverter happy with it? Like you said, all the pieces have to be happy. And so he said, well, okay, first of all, what we got to do is we got to add up things. So here, each of these panels, if you look at the spec sheet, where's it? What's it called? It's called right here.
Voltage maximum power point, VMP.
See where that's at? What's that say?
There it is. Voltage at Pmax, VMP.
What's the amount? Does it say, guys? Anybody? What's that?
37.18.
37.18.
Yep.
So Dave said, well, okay, it's great you want 14 panels, but what's 37 times 14? Well, and then if you look at the inverter specs, which you got this sheet here, the Danfoss thing, all right? Look at that, and we should find something similar to that on here, right, Dave?
37 times 14 is 518. 518 is above your normal operating range DC. It goes to 500 volts.
So if you look at the second section here where it says DC, the third item is normal operating range DC.
between 230 and 500. And so when I was talking with Dave on the phone, he said, look, we have to get this thing to get to 230 to make it turn on, and we can't go over 500.
Right.
So we gotta hit a sweet spot. So that's our range. So we couldn't put 2 panels in this thing, because that's only like, what, 60, 70,
70 volts.
70 volts or something. Well, that won't kick her on. All right there? And so we had to get in that sweet spot. Well, 14 is too much, as we just figured out.
In series, all in one series. is
All in one thing together is too much. So he says, well, wait a minute. What if we do half? All right, so what's 7 times 37?
half of that.
Half of that, so about 259
59.
or 260, right? Oh, but that means that we got to take 2, what we'll call strings, and put it in the inverter. Will the inverter handle it? Yeah.
We're above 230.
And we're above 230, and the inverter, in this case, this inverter will take up to 3 strings,
Yeah, it doesn't matter.
but it takes more than 1.
Yeah.
I mean, I'm assuming there might be inverters that only take 1 or something. You
Yeah,
know?
those are the small ones that only take 1.
So our inverter would take 2 strings. Cool, we can cover that. But then he says, well, now wait a minute. We got another element here too. What are going to be the amps? Again, we just talked about amps, right? We talked about the capacity. So we look at the solar panel specs again. The
7.8. Current at P max.
7.8 underneath. Yep. Okay. 7.8, right? On our spec sheet for the universal solar.
Yep. Now
So-
remember, that's at 70 degrees.
So at perfect temperature is our average temperature or whatever. So that means each of these panels, right? No, I'm not doing that right.
Yes, you are. Each panel,
It's pumping out 7.8 amps. Again, if I do that by 14 or whatever, I get,
no.
go ahead.
You're putting the panels in series so that the total loop is still 7.8 amps. All you're doing is building the voltage, but it's still putting 7 amps. Remember, power is volts times amps. $37 volts, 37 volts, 37 volts. Okay, we're going to build that up to 257 volts. But the amperage is the same through each one. So it's 257 volts times 7.8 amps is going to be 2,000 watts. That's parallel and series. It's a big electrical concept.
So 7.8 amps was okay, but then I have 2 strings. He talked about it before. Put those together, and I'm under the max for the inverter again.
Yeah, for amperage.
And the max,
21.
so down here, under DC, it says max input current, operating current is 21 amps in this particular 4.4.
And we're at 16 currently.
So we're at 16, and even if we up it by 20%, we still stay under, as he covered it before. So those were the things we kind of had to balance. That was one thing I did not understand. Like, well, grab some panels, plug them in, and let's flip her on, baby. Well, you got to balance it. And that was the thing that, so then they said, okay, well, we'll just cut this in 2 strings. That'll lower down our voltages, get us in the right range. And again, there was a kind of a balance there too. Because when we cut it, we had to still hit the turn-on voltage. So.
And during this discussion with Eric, we're really struggling because I didn't know what his goals were. And that's why Eric started out with what your goals are. What's the goal? And I didn't know what his goal was. All I knew is he's out there looking for panels, and I don't know what panels Eric's looking for. And I'm like, well, you gotta stay within P, volts times amps equals watts. So here's the inverter I can get you. You gotta stay below those watts. And Eric's new to this, so he's looking at all these different panel companies. And he's like, well, should I go with smaller panels or bigger panels or this poly or mono or thin film? There's just hundreds of options. And that's where you hit sort of the ocean of emotion
Oh, yeah.
kind of thing.
Well, it's just a difficult part of it. You don't know what to pick and stuff, and so that's the challenge. But Anyway, I just wanna point that out. Does that make sense to everybody? You kinda see the questions on that? Or Jim, yeah, you're.
Well, no, the difficult part is the electrical end of it. 'Cause
Yeah.
I haven't been trained
Right.
to get a handle on either series or probably all that kind of stuff. I mean, that's something where obviously your expertise is vital, but to understand it takes a little bit of time.
It's a different language.
Yeah, it's like.
You know, an accountant,
Yeah.
Mrs. Skelton,
Yeah.
it's a different language. She could talk to me for a day and I don't know what the terms mean. And I could talk to you for days about electricity, but I have to, the teacher has to put the terms in concrete concepts that you're gonna, and that's why I use the water and the hose.
Yeah.
Because having the idea of the flow and your inverter taking flow and the flow has to be right and all that stuff, I mean, I can understand that, but to actually work with the concrete part of it, it just takes a little bit of finagling, it takes a little bit of work.
It takes time to understand it.
Yeah,
My experience with this too, and this is where maybe people who see this on the internet or whatever from us, or other people that talk to, there are professionals in the field, and I don't take anything away from who design and set up and put out solar systems for residential use. They get paid well, and they should, because they can quickly come up with a solution because of their knowledge and experience and training that would work for a residential application. My experience going through this though is there's probably this basic range for residential, and if you got a little bit of expertise help, and you might have to pay for it even if you can get somebody that gives you that, you can take care of this stuff and hit the target. Because I think for somebody like David, this is simple, you hit the target. For me, it's simple to say, this is my goal, this is what I'm looking to do, and I know basically for a residential system to me, it doesn't look like it's very complex for those who know this stuff. Basically, it's gonna kind of fit in a general range. Commercial could be a whole different animal, but for residential, we're not, it's gonna be kind of, like you said, it's single phase, it's not three, all kinds of things don't come into play. So, I think this is the kind of thing where, you know, if you said, well, and I was like building off of people's work, okay, well, here we did a 4,000 watt system. You wanna tweak it a little bit, change it, but you could just stamp it, and it's pretty much gonna be the same thing. Now, if you wanna go to 8,000 watt system, you're gonna have to maybe get some more expertise in to design a system that'll work in those components that design it.
Or just put two of them in.
Or put two inverters, right, take the same system and double it with another inverter, yeah. And so, so anyway, that's kind of, I don't know if you would agree with that, but basically, and I'm not trying to say that this stuff is simple, I don't mean that, but realistically, you get the expertise in this part of it, and I think you got it licked. When we go to Mountie next week and talk about that, again, construction. For me or Jim, it's not a big deal for the construction part of it, and there, if you weren't very handy with that or were concerned about how that worked, again, that's easy to get the expertise, or get a carpenter, or get somebody to give you a design that you can follow and do yourself if you want to do it yourself. So
The key to it though is, the same concept I've tried presenting you today is, each piece has to be happy. And as you can see, there's lots of ways of doing it. There's lots of ways of making a mounting system, but each piece has to be happy. The unistrut has to be bolted at both ends. No, not just one. Why? Well, you get a hole in it.
not gonna be happy.
You have, and as Eric started out, is you have to have a goal. Well, the goal here, next week for Eric is I gotta make something that's gonna withstand the wind. And as Eric's gonna explain, wind is very powerful.
and it's going to withstand my pocketbook. So, the other thing that I wanted to point out, a couple other things, so, we did have a purpose and a plan and a goal in mind. Again, we're working through this design, and we're doing these kinds of things, and as I mentioned, what we call this is a one-line diagram. That's this diagram that actually, again, Mr. Martindale had put together for me, because I don't know what a one-line I do now. After looking at this, like, oh, it makes a lot of sense, yeah, I understand that. So being that I've worked with electrical systems, residential household systems, so but need a one-line diagram. One of the main reasons why you need a one-line diagram is because, in our case here in Wisconsin, and where we're at in southern Wisconsin, Alliant Energy is our utility. And if you want to put a solar system in, if you look up online at Alliant's website, they got a whole thing on renewable energy if you want to do it, and they say in that, you know, contact us early on. I looked at their information and I read through it, and so I wasn't wasting time, and I didn't spend any money yet. By the way, at this point in my process, I've not written a check, okay? So the reason they want you to do that is because, back to what Mr. Martindale said, is look, demarcation, from here up, it's theirs. And they're not gonna let you throw the switch and get on their system unless they're happy with it. So if you spend a bunch of money and say, hey, I got a solar system, I'm ready to flip the switch, and they go, hey, that's great, but guess what? It don't meet our specs. Sorry, you spent all that money.
This is a real issue, okay? People can spend hundreds of thousands of dollars building a power plant and not get the utility permission and have the utility shut down. I've been working in this industry 27 years. The utility is a huge battle. I personally had a project in downtown Chicago, the utility wanted to shut down, and I told them point blank, no, we're going to build this. And they caved.
Wow.
Negotiation is important. And Eric's, your main mission is negotiation. So,
Well, yeah,
in a certain sense.
yeah, I
So-
suppose, yeah. But
Learning how to handle people is way more difficult than understanding the wire size.
I agree with that. Yeah. They're discreet. The wire size is discreet. But so with a power company, and the nice thing about it, unlike in a big commercial system, the residential thing, they made it pretty much in a can. If it fits within this can, you're good to go. So you start out early with them. Now I didn't want to waste their time and my time. I made a call early on, kind of got a feel for what they were looking for, and then I left that because I want to see if this was even feasible and what it was going to look like before I went through that process.
Can I interrupt?
Yeah.
The utility has its parameters of guidelines. They don't want a power plant in a residential neighborhood that can produce more than 15% of the wire's size going to that neighborhood. The reason that is they don't want, if the telephone pole is right here, and the only thing on that power line is these two houses, let's say. Now Eric's produced a power plant that's gonna take up 50% of what's on that particular line. And if that line gets cut, and Eric is able to island, is the technical term, now Eric's producing power for himself and his neighbor, and the utility guy comes by, and he's supposed to have a dead line, and he's gonna fix it, and the line's wide, the electrician's gonna get hurt. Don't want islanding to happen, meaning independent power production without the utility is unsafe, because they can reclose those wires out of phase or hurt themselves. So they have, my point is that the utility cell company themselves has guidelines they need to stay within. It's typically 15% of the capacity of the line size going to a particular area where there's a power plant. If it exceeds that, then they have to put monitoring equipment back on their equipment so that they know that you're on before they work. So there's technical reasons why they want to have,
Sure.
give you
And
permission.
again, it's simplified for us all in this. UL listed inverter device, which immediately shuts down if power is not sensed on the system. And so that's, I guess what I would say is that's the, but, so Alliant Energy, I've gone to the stage of, I know my return on investment is going to be good. I have a basic, and even more than basic, understanding of the design system. I've looked at what Alliant would want from me if I was going to do a system, and they have online, you can get a, it's called a standard distributed generation application form. And so this is a form, and there's an application I had to fill out, and I had sent to them a number of things, some of which is in front of you, but the application I filled out, which was several pages, it wasn't complex, it was very straightforward for me to do too. And I don't know if I had to ask any questions of Mr. Martindale, except for they asked for the kind of inverter I'd be using, I had to put that there. In addition, they wanted the UL statement of compliance or certificate of compliance for the inverter. Why? Why would they want this? What does this tell them about the inverter? Why would they want a UL? By the way, do you know what Underwriters Laboratory is? Any young guys? Anybody? You know what UL is? Nobody? Okay. UL is?
UL is a testing agency that tests the piece of equipment for compliance to the standards.
Yep.
So everybody across the United States, manufacturers and consumers look to UL to say, hey, did you guys test this thing? Is it properly built for the application it's meant for?
So they made a thing that was outside of any one individual company so that you can't have any shenanigans or anything else, but you got one outside entity that's testing. So they should have no vested interest if the toaster is garbage or not, because they're not a toaster manufacturer, they're not trying to sell toasters. So, and then we had to provide that which this meets the standard, which tells the power company, okay, this Danfoss inverter will do what it's supposed to do, which we're happy with and makes us happy. Then I had to provide a certificate of insurance that we have, homeowners insurance and so forth. We had to provide a one-line diagram. That was the most difficult thing for me because I did not know how to make this bugger. I looked online, I saw what lines were and understood that, but so what? That doesn't mean nothing to me. I can't do this. Mr. Martindale could do that. He helped me with that. And I had I think I gave you a lot plan. I had that just in case because I figured I would need that for building permitting and land use and zoning in the township. I don't remember if I had to give this to Alliant Energy or not. Yeah, I did have to give this. Alliant Energy requires a site plan with disconnect. If you notice on the printout, it says down here, solar array with disconnect. So they wanted to know where the disconnect was. The Danfoss inverter actually has a switch on it that is the disconnect. What that means is they want to know that you can go up and you can cut off the solar system from that, a disconnect.
There's another reason the disconnect is important. PV panels are becoming more and more popular, and the fire departments respond to buildings, and if they see PV panels on the roof, one of their first things is they're going to yank the meter off the house if there's a fire in the house, because they're going to be pouring water on the house.
Yep.
Okay, water and electricity don't mix. Water does conduct electricity, and all of a sudden the firemen they're standing in 120 volt water. So they're going to want to shut off the sources of power. They're going to shut the gas off and the electric by pulling the meter or pulling the cutouts at the poles. Oh, solar panels. Uh-oh, I can't throw a tarp over the panels. They're going to find they want to shut that inverter disconnect off.
Because in their mind, they don't know that this inverter would shut down necessarily. So we got the power coming in here to the house shut off. We still have power coming to the house from here. So that could be problematic. In our case, with this Danfoss inverter, again, they don't know that, but it would not be supplying power to the house because power is not on the grid. And so we had to provide them with those that application, which I did. They have an engineer, they reviewed it, and they approved it, okay? And that's where I am at this point in the design. I've got a basic understanding of what I'm going to do. I've got a design of the system. I have an application approved by the power company. And for me, I was now in go mode. I was now at the point where the only thing I needed to do now was to get the governing entities, in our case the county land use permit and the township building permit. Now, I didn't anticipate not being able to get those, I just had to be able to get those. I had to get those permittings. And so that was my next step, and so I was ready now to cut checks. I was now ready to spend money because now I knew that I had a system I was going to go forward on and Alliant approved it. And then I actually went to the governing bodies, I think I mentioned last time, and they did not require a building permit and they did not require a land use permit in this case. But I was really in go mode. So then I began the purchase of equipment that I needed and started sourcing that and started planning for that.
And last Wednesday, or this last Wednesday, you saw some of that equipment.
Yeah, we did, yeah, when we went to the, when we went down to the solar plant, yeah. I didn't see my pile of pallets, but
I
I
did.
saw thousands of others. Did you see that? Yeah, so, good. So, any other questions about that element? Any other thoughts?
Is there any, anything new that you can think of from your solar tour that you didn't think of while you were there?
Yeah, good question. Good, well, next time, what we're gonna do is we're actually gonna look at a little bit more of design. I did wanna talk through about how to actually physically build this system, and we gotta look at that plan. And we have that plan, because before we build it, we should have a plan on what we're building and how we're gonna build it. It's the construction side, the mounting side, I'll call it, of the system, and how we're gonna mount it to, where we're gonna mount it, and how we're gonna mount it.
Are you
So,
gonna have your parts and pieces by next Saturday?
I have most, I don't know some of the elements, I don't know if I'll get all the shipment of things that I need, so. I gotta work with trucking on that, so. I didn't get it this week, but hopefully next week I'll get it, so. I need to have it pretty soon here. And then after next week, of course, the following week, I have an opportunity for you guys to get your hands involved in actually constructing or being part of it and putting this together, and so the following Saturday, we'll be doing construction of it, and it will not all get done on that Saturday, but, so appreciate the help if you want to help and have a little fun out there. You know, it's always fun using a shovel. I just think everybody should look forward to the digging, because digging is so fun, what a joy, but there's more than just digging. So. All right, great.
Digging is fun when you can splatter mud on people.
What's that?
Digging is fun when you can splatter mud on people.
Well, but you know what, we can do that too, that's all right. We can,
Make sure Mark is ready before we.
make sure Mark is ready, yeah. Yeah, well, you know, one-armed bandit, he'll have to maybe not do shoveling, there might be other things that he's gonna have to do. So.
Do you have any completion date requirements from the utility?
No, there's no completion date requirements.
Regardless of that anyway.
The only requirements in terms of timing would be is if you got a building permit, usually generally around here, they're about 2 years in time frame for building permits. The utility wanted to know generally what time frame we were gonna go live. And then, I need to contact them to schedule when I'm ready for their meter tech to come out to test the system.
Really?
Yeah, they wanna test the system. They wanna have a meter tech on hand to test the system. And basically what they wanna do is what do you think they would wanna do? What would the power company want to test? What would be the big thing that they would wanna test? If they wanna test this system, what do they care about, do you think? We've been talking about here. What do you think is the most important thing to them to test really at this point? And what do they wanna know, Jim? Will shut down. And so to do that, what they do is they cut the power, they simulate a cut in power, and they want to see the inverter go off. That's it. And if they see that, they're happy.
Concerned about their line.
Yeah, right, for safety and stuff. Yep. So that's exactly it. That's all we need to do. So. All right, good. Well, praise God. Thanks for coming again today, and look forward to seeing you guys next week. And we will be on to our next step.